Welcome back, ladies and gentlemen. We are going to be talking about inverses of functions today. So there are two things that you are responsible for learning from this video. The first thing that you need to learn is you need to learn to figure out what is an inverse. We need to get a definition. After we know what inverses are, we're going to learn how to find them if I give you an equation. Okay? So given the original function, you need to be able to find an inverse. And if I give you a graph, you need to be able to find the inverse of that graph as well. Okay. All right, so let's start by talking about what is an inverse function. So an inverse function is just a function that undoes another function, and they're said to be inverses of each other. So let's talk about an example. Let's take our favorite function, f of x equals x plus 3. So all this function does is take our input and adds 3 to it. So if I want the inverse function, it has to undo this adding 3. So the inverse function, we could call it g of x, would take an input and then subtract 3. Okay, so that's all they do, is they're functions that are going to undo each other. If we think back to our analogy of having a function machine, right? Here's f, and we're going to give it an input. It's going to go in there, and then we'll get an output. Let's call it y. Okay. So I feed it into f, I get y. Then if I run y back through the inverse, g, then what that's going to do is take this y and it's going to turn it back into x. It's going to undo what this f function just did. Okay, so we're just talking about functions, and then the other function that goes with it that'll undo that function. Okay. Last thing on this slide I want to talk about is just some notation stuff, because math notation can be a little confusing. If you see a function written like this, where it has a -1 exponent between the name of the function, f, and the input, that does not mean 1 over f of x. We're not using the exponent rules here. If I wanted the reciprocal of f, that would be f of x to the -1, like that. The -1 would go after the x. What this means right here, the way you would say this out loud, so if you're talking to like a college professor and you want to sound intelligent, the way you say this out loud is the inverse of f. Okay, so if you see this little -1, do not go to your exponent rules. It's just notation letting you know this is the inverse of f, or this is the function that will undo the f function. Okay, so we're going to talk about this slide really quick because it's important, but unfortunately it's not on your homework. They don't test to see if you know this. So this is kind of a nice to know. Right? It's not necessary. It's not going to be on the test, but it is nice to know for when you go to college and things like that. It'll help you be a little bit more prepared. Keep in mind that this year you're in a kind of weird online coronavirus pandemic kind of abridged curriculum. So just understand that we're cutting out some of the extra stuff to keep it succinct. But you're in honor, so here's some extra stuff. So if we think about the domain of x, domain, again, are just your inputs, so your x's. The domain of f of x will be the range, that is the outputs, of the inverse of f. Likewise, the range, so the outputs of our original function will be the domain or the inputs of the inverse function. So again, math definitions can be kind of convoluted and not necessarily straightforward, so let's talk about an example. Let's say I have a function f. Here are my inputs, the 1 through 3, and here are the outputs, the things I get when I plug them in, going this way. Okay, so when I plug in 0, I get 3. When I plug in 1, I get 4, and so on. This is just our f of x equals x plus 3. We're adding 3. So what this definition up here means is if I take the range of my original function, the outputs, and I use that as the inputs for its inverse, then I should get the original inputs back. So if I take my outputs, 3, 4, 5, and 6, and I plug them into the inverse function, it's going to undo the adding 3, and then the outputs will be my original inputs. So they're just switched. These two columns get reversed when we look at the inverse of a function. Okay, now you're going to say, how do I do the inverse though, Mr. Barton? How do I find my own inverse? You're really smart and you know how to do it, but I need to know how to so I can pass my classes. So here are some steps that we can follow to find an inverse algebraically. That means we're going to do algebra. We're going to do inverse operations to solve for something. So step 1 is if there is an f of x or g of x or h of x in the problem, replace that with y, just because we don't want to have to rewrite this thing 100 times. Mathematicians are lazy. So it means y, so just put a y in there so you don't have to move as much stuff around. Okay. The next thing we're going to do is take the position of only the x and only the y in the equation and swap them. Don't move anything else. No exponents, no radicals, no adding, no subtracting, no nothing. You're only switching the position of the letters in the equation. Okay. Step 3 is the easy part. That's the math, where you solve for y. So now you're going to get y by itself. And then step 4 is just good note keeping or good organization. Because we turned this f of x into a y here, now we need to change it back. And because we just found our inverse, right, we're finding an inverse, we don't have f anymore. We're going to end up with the inverse of f. Okay, so let's go look at some examples. Here's the first function we're going to find our inverse of. So I see I have an f of x here. I'm going to replace that with a y. Now step 2 says we need to switch the position of x and y in our function. So I'm just going to rewrite it, switching where these two letters are located. So x equals 4y minus 1 over 3. Now step 3 is we want to get this y by itself. So what we're going to do is we're going to get rid of this divide by 3 by multiplying both sides by 3. So these 3's cancel each other out. On the left side, we have 3x, and on the right side, because the denominator canceled, we don't need to write this fraction anymore, and we're left with 4y minus 1. Now we need to still get the y by itself, so we're going to subtract the 1 over. I'm sorry, I'm being lazy. We need to do the opposite. So because it's minus 1, we're going to add 1 to both sides. There we go. So negative 1 and plus 1 cancel. Those go away. So we just have 4y on the left. And then, on the right. And on the left here, 3x plus 1. Because this has an x and this doesn't, they're not like terms. So they need to stay separate. So it's just going to be 3x plus 1. Now our last step is we need to get rid of this 4. And the math operation the 4 is doing is multiplying to the y. So we're going to divide this side by 4, and we're going to divide this side by 4. You need to make sure you do the entire side on the left. So the 4's cancel, and on the right side, we're left with y. And on the left, 4 doesn't go into 3 or 1, so we can't reduce this, so we'll just leave it like that. So this is 3x plus 1 all over 4. And our last step, because we started with our problem in function notation, we have to put it back in function notation. So we're going to change our y into the inverse of f because we just found an inverse. Remember, make sure the minus 1 is between the f and the input, and then just copy this side. Okay, so there's one example. Let's do one more just to make sure we have the idea. And if you need more practice than that, go ahead and rewind the video and rewatch it. So again, the first thing we're going to do is change our f of x to a y for simplicity. Then we're going to reverse the position of x and y in the function. So we get x equals 1/2 y plus 6. All right. Now we need to solve for y. So we're going to add 6. I'm sorry, I almost did it again. We're going to subtract 6 from both sides. So we're going to undo this function. So -6 and +6 cancel each other out. So we're left with our 1/2 y on the right. There we go. And x and -6 are not like terms, so we keep them separate just like before and bring them both down. So this could be x minus 6. I'm writing it in standard form. Now, we need to get rid of this 1/2, and it's multiplying to y. We could divide by 1/2 to undo the multiply, but remember, you can't really divide by a fraction. So what we do to divide by a fraction instead is we multiply by the reciprocal. So we're going to multiply by 2/1. On the left side, make sure you multiply by the 2, because 2/1 reduces to 2. Make sure you multiply the 2 to everything. We're going to distribute it on this side. Whatever you do on one side, you have to do to the entire other side. So 2/1 times 1/2. 2 times 1/2 is 1, and they cancel. So on the right side, we're left with just y. On the left side, we're distributing the 2. So 2 times x is 2x. 2 times -6 is -12. And then just like on the left, we can't leave it as y because our original problem was in function notation. So we change our y into the inverse of f. And then this is our final answer. Okay, so there's 2 examples on how to algebraically solve for an inverse. All right, let's talk about one more definition, just because this might not be immediately obvious, and then we'll do a really easy example. So this is a composition function, which is the first thing we learned in this class. It's saying take the inverse of f and plug it into f. And when you do that, your answer will just be plain old x. So remember, when we said we do composition functions, that means we make a new function that does one and then immediately does the other without getting the middle step. So if I'm going to do a function and then do its inverse immediately after, I'm going to do something and then immediately undo it. So whatever my original input is, it's just going to give me that back. So let's look at this easy example just to see how that works. If I want to do f of the inverse of f, like that, these two are the same thing, they're just different notations. I'm going to write the outside function first and then plug the inside function into the x. So what that's going to look like, I'm going to write the f of x, where the x's put some parentheses, plus 7. And then we're going to take the inside function and plug it into the parentheses. So we have x minus 7. Now we need to simplify this. These parentheses aren't doing anything. There's no coefficient here that we need to distribute in. There's no dividing that means I have to do it to both of these. These parentheses are just for decoration. So we could treat this like x minus 7 plus 7. And then we combine our like terms. -7 plus 7 is 0. So these cancel out, and you're left with just x. Okay, so if you ever do a composite function with a function and its inverse, they'll cancel each other out and just give you x. All right. The last thing we have to talk about today, or I'm sorry, I'm getting ahead of myself. There's 2 more things we have to talk about. The first is it allowed to have an inverse? And the second is, how do I get an inverse graph? So in order for a function to have an inverse, it must be 1 to 1. So let's think back to our last video we watched. This means that it passes the horizontal line test. Okay, so if you draw a horizontal line on your function and then scan it, it should never touch more than once. If it does, it's not one-to-one. And what that's going to mean for us is that there isn't an inverse. Okay, so let's look at this example right here and kind of see why that is. So if I graph this, it's going to look like this. That's just our basic parabola function. Okay. If I scan this with my horizontal line, we can see that this is touching twice. If I find the inverse of this function really quickly, this is going to be x equals y squared when I switch our x and our y. I'm going to solve for y, so I'm going to take a square root to get rid of our squared. And remember, when you take a square root, you get a plus or minus in front. So we get y equals plus or minus the square root of x. The square root of x looks like, whoops, sorry, that. And then the minus of that looks like this. So the reason functions that aren't one-to-one don't have an inverse isn't because we can't find a graph. It's because when we look at that graph, it fails the vertical line test. So really, if the original function isn't one-to-one, when we inverse it, the new one won't be a function, right? It just fails the vertical line test. Okay. So one way we can fix this is we can put a restraint on it. We can say that I want y equals x squared, but I only want to look at it when x is greater than or equal to 0. So what that does is it erases this whole negative side. So if I inverse this half, I'll only get the positive half of the square root. And now this new function, where we're only looking at half of it, passes our vertical line test. So if you have a function that isn't one-to-one and you want to find an inverse, we might have to limit where we're looking at it. Okay. So now you're going to say, wait, how'd you find that inverse so fast? Let's look at, oh, I'm sorry, I'm getting ahead of myself again. So let's look at these functions and just say, do they have an inverse or not? Okay. If we look at this function, we want to look at a graph so we can do our horizontal line test to check if it's one-to-one. If it is one-to-one, then it will be a function, or it will have a function that's an inverse. So if we look at f of x equals x cubed plus 1, the first thing you want to do is graph that. I would just plug it into Desmos or a graphing calculator so you can look at it. So we'll pull this. Here's our graph. If we do our horizontal line test on this, we can see that the original function, f of x equals x cubed plus 1, will pass our horizontal line test. So that means that this will have an inverse function because it's one-to-one. Okay. If we look at g of x equals x squared minus x, let's think about this for a second. What do x squareds look like? What kind of functions are those? Think about it. Chew on it for a second. Oh, that's right, Mr. Barton. They're parabolas. So without graphing it, you know this will be a parabola. Will that pass the horizontal line test? No, of course not. But here is the professionally made graph. So if we take our horizontal line, that's not a good one. Let's move that out of the way. If we take a horizontal line and scan this, we can see it fails the horizontal line test. So its inverse will not be a function. Okay. Last one, the square root of x. If we look at that graph, we can see that this one will pass the horizontal line test. So this thing will have an inverse that is a function. Okay. The last thing for real this time that we have to talk about is finding an inverse graphically. This is easier than the algebraic form, so don't panic. The first thing you need to do is find several ordered pairs. What several means is as many as you need. I'm going to say at least 3. But the more curvy your graph is, the more points you want to get on this first step. Okay. Once you have your list of points, we're going to reverse the order of the numbers. Do not change signs. Don't change them to negatives. Don't turn them into fractions. Just take these two numbers and switch their position in the ordered pair. This is your inverse. This goes back to this nice to know idea. The domain of the original will be the range of the inverse, and the range of the original will be the domain of the inverse. So that's all we're doing with graphing, is we're taking the domain, or the x's, and turning them into y's, and we're taking the y's and turning them into x's. Once you have your new points, the last step is to just plot them. Put them on the graph, and then you're done. All right. So let's look at 2 examples. This first one is super, super easy. Always make sure you're getting points that you can read off very clearly. This is a bad point because it's in between -1 and -2, so we'd have to guess at that. So don't use that point. That's a bad point. Use probably this point looks good. This point looks pretty good. Are there any others? Maybe that one? Those all look good. So the ordered pair here is -1, 2, 3, 4, 5, 6, 7, 1. The ordered pair here is 0, -1, 2. And the ordered pair right here is 2, -3. So to find our inverse, what we're going to do is reverse these 3 ordered pairs. So -7, 1 turns into 1, -7. 0, -2 turns into -2, 0. And +2, -3 turns into -3, 2. Now we are going to graph these new inverse points to get our inverse graph. So we're going to go 1, -1, 2, 3, 4, 5, 6, 7. -2, 0. So -2, 0. And -3, 2. 1, 2, 3, 1, 2. And then we're going to put a line through them. Let's try and make it as straight as possible. I don't know quite. I'll just move this one. Watch this. Ah, almost perfect. There we go. Okay. So that is our inverse graph, this blue line. There is technically another way you can do this, and your Algebra 2 teachers may have showed you this. If you draw a diagonal line this way, all of your points are mirrored across this line. So if you go perfectly perpendicular to it, so you go diagonally through each point, we go 1, 2, 3, 4. So this is 4 above the line. We're going to go 4 below the line. 1, 2, 3, 4. Oh, look, there's our inverse point. So if you prefer, you can draw the diagonal line and then count perpendicular to it, going diagonal. And then that'll get you your inverse points as well. All right, let's look at one more that's a little weirder. So if you have a graph that has a vertex, what that means is it just has a stopping point. Always include that vertex as one of the points you choose because it's a really important point. If our graph starts somewhere, we want to make sure our new inverse graph starts at the appropriate location. Then we're going to pick a couple more points that look easy for us to read. We're going to find the ordered pairs. So this is -5, -2, -4, -1, -1, 0, and 4, 1. And then we're going to take these ordered pairs and find their inverses. They're all connected. All right. So this one would be -1, -4. This one will be -2, -5. This one will be 0, -1. And this point will be 1, 4. Then we graph our new inverse points and call it a day. So we go left 1 down 4, left 2 down 5, 0, -1, and then 1, 4. Okay. Whatever point you use to get that vertex, the -5, -2, when you inverse that, this one will be your new vertex right here. So this is our stopping point. Your graph needs to stop there. If it doesn't stop there, it's wrong. It's not going to be a big deal on your homework because it's multiple choice, but you should know. All right. I believe that is all you need to know about inverses. If you have any questions, go back and watch the video a second time, or maybe pause it, rewind just one part and watch that part again. Or if you're really struggling, hop in WebEx and say, Mr. Barton, I need some help.